In this recording, there is example on absolute ceiling, and also we will briefly look at time to climb, which is very trivial. So here is familiar aircraft, that's our prop aircraft. We will need all this data, and objective is to calculate absolute ceiling. You can do it in tabulated way. You can just figure out what is maximum rate of climb for various altitudes, find gradient of this line, which is assumed to be just linear relation, and then figure out what is absolute ceiling. In this case, we use derived equation, so what we derived in previous recording, and the process is very, very simple. We simply figure out all bits and pieces in this equation one by one. So aspect ratio, power available from given data. Here is power loading. You can calculate it separately, or you can just sub it in the equation. And the rest of the stuff, all those various square roots, it is very straightforward solution. So just estimate, and then sub it in, and then you calculate it. Obviously, it is not very convenient to do by hand. The best approach is to write a little script in MATLAB. So out of all this, we get following result, that maximum ceiling for this particular type of the aircraft is 25,850 feet. Now, time to climb. It is time to go from position 1 to position 2 in vertical direction. So now we are going to integrate both sides. We integrate both sides, and here we will have obviously time to go from h1 to h2. And on right hand side we have integration over vertical displacement. Rate of climb is sitting in the denominator. Note that rate of climb is a function, and as a result of all those integrations we will get nonlinear relations. If we are looking at motion from sea level, then things become simpler, and limits on integral will be from 0 to final position. If we want to estimate it graphically, then we can plot inverse of rate of climb and then get area under the curve. And here it is. So on vertical axis we have inverse of rate of climb, on horizontal axis we have altitude.